Welcome back to Elementary Statistics. In this video, I'm going to introduce you to a student's t-test. I love the history of this particular statistical tool because it talks about the power struggle between academia and private industry. William Seeley Gosset was the brewmaster of Guinness Brewery in Dublin, Ireland. One of his jobs was to develop tests and tools to verify that the product they were producing, Guinness beer, was at the same standard in every batch. In order to do that, he developed some mathematical tools. He called these tools the t-test. But because he developed these tools while working for Guinness and while on company time, this was considered to be company property and proprietary information, not something that William Seeley Gosset could use on his own. And so he created a pseudonym for himself, a student, and decided to publish it anyway, because he felt that the continued discourse and discussion in the public of the development of statistics was the greater good. And so sometimes you'll see this simply called the t-distribution or the t-test. But if you see it called student's t-test or a student's t-test, it's in honor of William Seeley Gosset, who broke the regulations and risked repercussions at his job and career in order to further the advancement of statistics. Let me get my head out of the way and let's establish a little bit of why students' t-test is so valuable. We have been working so far with the z-score and the z-test. And the z-score gave us this way of working with confidence, and we built off from that to test hypotheses, where if we know the mean of a sample, the size of the sample, and the standard deviation of the population, we get an estimator for the mean of the population. The problem with the z-test is that we have a population parameter on the right-hand side. It would be better if we could find a way of first estimating the standard deviation of the population using the standard deviation of the sample, and then using that instead. And that's exactly what the t-test does. In the t-test, mu is going to be equal to x bar plus or minus this new thing we're going to call t, which we multiply by s over the square root of n. For the t-test, we have one population parameter on one side of the equation, and on the other side of the equation, everything is a sample statistic. So we can calculate all of this based on our sample. When it comes to the t-test, even more than with the z-test, sample size is important. The larger the sample size, the better the approximation that the t-test gives us to the standard deviation of the population. And in fact, when we start looking at the data on the t-test, what you're going to find is that if you take a particularly large n, in the case of the table that I have on hand, that's an n significantly larger than 1,000, but still something that is manageable in some circumstances, at that point, the values for t are exactly the values for z. The value of the t-test is that it gives us a tool for approximating z times the population standard deviation sigma as t times the sample standard deviation s. In order to do that, we have to have a different value of t based on the size of the population. Here's where things start to get a little bit complicated. Not difficult, just we want to be precise in what we are doing. That complication is in what we call degrees of freedom. And the idea of a degree of freedom is when you calculate the things that you have calculated. In the case that we are going to be using, we want to use X bar as an estimator. The question that degrees of freedom is asking is, of the n samples in your distribution, how many can you change and keep the same value of X bar? Or to give title, how many do you have the freedom to choose? Right. So for example, if I know that X bar is 10 and n is 5, if I make my distribution start with a 1, I can still ensure that I'm going to have a mean of 10. If my next value is 12, I can still ensure that I have a mean of 10. If my next value is 25, I can still ensure that. If my next value is 9, I'm still okay. But at this point, I have to stop. Because once I pick the next value, my mean is set. So if I add 1 plus 12 plus 25 plus 9, I get 47. In order to ensure that my mean is 10, when I add all 5 numbers together, I need to get 50. That means that the only option for that last value is 3. The first 4 values in this set, I have the freedom to choose whatever I want. The last value, I do not. So the degrees of freedom in this case is 4. For what we are doing right now, using the t-test to use the mean of a sample as an estimator for the mean of a population, it will always be the case that the degrees of freedom is n minus 1. There are other tests that you can do with the student t-distribution where the degree of freedom will change. But for this one, the degree of freedom is always n minus 1. The fact that there are other tests you can do where the degrees of freedom calculation changes is why we call it something different. In another test, we would have a different way of calculating this. And I know that for me as a student, that was always a frustration. We always use the same calculation for degrees of freedom. Why don't we just give it a different name? Why don't we just put n on the table instead? And again, the reason is that there are other tests that use the same distribution that have different calculations for the degrees of freedom. Even though we won't be talking about them this semester, it doesn't mean that they aren't there. So we have this bit of extra complication just for the sake of it, except that there is a good reason. All right, so let's look at a particular example. And as we have talked about, you can talk about the alpha value, your level of significance, if you are talking about a statistical hypothesis test. Or you can talk about your percent confidence if you are talking about a confidence interval and an estimate of the value without any predictive quality to it. But the calculations are the same in either case. Alpha equals 0.05 is equivalent to a 95% confidence interval. We could do other intervals if we wanted to, but this is good enough for now. All right, let's look at some particular data. And again, I'm not going to give you the distribution. I'm not going to ask you to calculate the mean and standard deviation right now because that's kind of boring. We've done that. I trust that you know how to do that. But let's take a look at a distribution where we have that X bar is 27, S is 3.5, and N is 23. All right. So we collected 23 data points. We calculated the mean and the standard deviation of those 23 data points. We got that the mean was 27. We got that the standard deviation was 3.5. In order to use the t-distribution table, we need to have our alpha value, and many but not all t-distributions will look separately at a two-tailed or a one-tailed distribution, so it does have to be specified. I am only going to be looking at two-tailed distributions, but you might see one-tailed distributions elsewhere. We need to know the degrees of freedom, which is our n 23 minus 1, in this case 22. With that information, we can go to a t-score table or a t-distribution table like this one. And this looks very different from the z-score table because we have to look at different t-values depending on the degrees of freedom, and there's a lot of options for degrees of freedom. So looking down the first column, you see df, the degrees of freedom value. We want to go down that column until we find 22. Then we want to go across that row until we find our alpha value. And again, depending on which t-distribution table you are looking at, the headings here can look a little bit different. In this particular table, at the top row, you can see that it's labeled as cumulative probability. This is your confidence interval. So if we're looking for a 95% confidence interval, we're looking at t equals 0.95. If we're looking for a one-tailed test, we're looking here. If we're looking for a two-tailed test, we're looking here. Right? Depending on what you are given, that changes what we're looking for. I'm generally going to be looking at the alpha values That's the thing that is most commonly available in all t-tables. And so I'm looking at this column where alpha is 0.05. I'm looking at this row where df is 22, and I get that the t-value is 1.717. So I come back to my table and I write down that t is 1.717. Then what I do next depends on if I am looking for a confidence interval or if I'm looking at a hypothesis test. I think that the hypothesis test is a little bit more interesting. The null hypothesis might be that mu is equal to 24, and then the null hypothesis is that mu is not equal to 24. We construct our margin of error, which is that mu is equal to x bar plus or minus t times s over the square root of n. We plug in all of our values. X bar is 27. T is 1.717. S is 3.5. N is 23. And let's move this over to the other side of the screen. So that I can bring my calculator up without it getting in the way. I'm going to start by calculating the margin of error. 1.717 times 3.5 divided by the square root of 23. My calculator gives me 1.253. So we get that mu is equal to 27 plus or minus 1.253. That seems like a good place to round this. Then, using my plus or minus, 27 minus 1.253 is 25.747. And 27 plus 1.253 is 28.253. Our hypothesis test, remember it's off the screen now. The null hypothesis was that mu is equal to 24. 24 is not in this interval. So we will reject the null hypothesis with alpha equals 0.05 and say that mu is not 24, right? The mean of this population is not 24. If there was a particular situation we were looking at, then we might have more detail to say here, but I'm looking at a very abstract situation just to walk through the calculations with you. We've already talked about how to look at a problem and turn it into a situation involving confidence intervals, how to look at a problem and turn it into a situation involving hypothesis testing. That doesn't change here. The only thing that changes is we have a new tool to put in our toolbox on the situations where we do not know the population of the mean. With that, I'm going to wrap up this video. Thanks as always for joining me. I'll see you next time.